Okay, I think we're now live on YouTube. Hi, Omer.
Are we just joining? Everything going smoothly? It seems.
I believe so. Just setting the setting everything on YouTube the way I like.
Better keep talking so that it will capture.
One thing that I haven't quite had the energy to do, but that I thought would be good service would be, so like, for example, yesterday in JC's lecture, there was some inequality in a statement that he corrected like half an hour later.
Yes.
And I could just go into the live chat or the permanent chat of YouTube and post the correction to that so that people aren't confused if they're watching along. They don't have to wait the half hour for the correction.
So this has the effect that when someone is watching the video, they get the comment at that time?
I think there is a way to do that, but I was just thinking like as a comment below the video, like in the chat,
okay.
Which is easier. I mean, I have that chat turned off, but administrators or like the owner can still post chat even if other people can't. So.
Right.
Anyway,
I think there's also a way to have some message pop up on the video at a specific time.
Yeah, there is, except that they've changed. They made it harder to do that last year for some reason. Like YouTube changes its studio settings every few months, and I specifically remember them making it harder to do those overlays. But anyway, I guess we should get started.
Yes, I guess it's a good time. So we're all here for the third and final talk in Sarah's mini course. And yes, please to get started.
Okay. Can you see my mouse? Yeah.
Yes.
Okay, great. Okay, so thanks for coming to the last lecture. So just to recap, last time we were talking about the Brownian bees process, which is a particle system consisting of n particles moving around in RD according to independent Brownian motions and branching into two particles at rate 1. And whenever a particle branches, then the particle in the system that's furthest from the origin in terms of the L2 norm, that particle is killed. So there are always exactly n particles in the system at all times. So to remind you of the notation, so we wrote xn of t for the vector of particle positions in RD for the Brownian bees at time t. We wrote mnt for the maximum particle distance from the origin at time t, and we're always writing this norm to mean the L2 norm. We wrote mu n of t and dx for the empirical measure of the particles at time t. So we gave each particle a mass 1 over n, and then summed over all the particles and put a point mass at the location of the kth particle at time t. And we wrote fn of t and r for 1 over n times the number of particles that are in the ball of radius r at time t. And then to remind you of the results that I talked about last time, so they're sort of summarized in these boxes. So in particular, we talked about the proof of the hydrodynamic limit result that said that when we take the Brownian bees particle configuration, we fix a time t, but we let n go to infinity, then the density of the particles converges to the solution of a free boundary problem. So the plan for today is that I'm going to say a bit about the proof of the result that says that solutions of the free boundary problem converge to the steady state solution of the free boundary problem. And I'm also going to say a bit about the proof of a long-term behavior result for the Brownian bees. So essentially a result that goes from this to this. So that says that if n is very large and t is large, then with high probability the density of the particles in the Brownian bees is close to capital U, and the maximum distance from the origin is close to R infinity. And then after those proofs, I'm going to move on to a sort of overview of some results and conjectures about some other branching selection systems. So there are just a couple of things from last time that I'm going to use this time. So the first one is our one-dimensional hydrodynamic limit result. So that said that there's a positive constant C1, such that if n is large enough, then if we fix a time t and we take a vector xn in Rd to the n, then if we let Vn and Rn solve our one-dimensional free boundary problem with initial condition given by V0 of R is Fn of 0 in R, so the initial condition is determined by the initial particle configuration, then if we condition on the Brownian-Bees particle configuration at time 0 being given by Xn, then we can say that the probability that the supremum over R of the difference between Fn at time t and Vn at time t is bigger than something very small. That probability is very small. So we're saying that with very high probability, Fn is very close to a solution of the free boundary problem. And what's going to be useful to us today is that even though the initial particle configuration Xn is important for determining the solution of the free boundary problem Vn, the bound on the difference between Fn and Vn doesn't depend on the choice of Xn. So these two things don't depend on Xn. And then the other thing that we're going to use is that I said that we could couple our Brownian-Bees with a d-dimensional branching Brownian motion. So we could couple them in such a way that we start with our branching Brownian motion, and then we successively kill particles to produce our Brownian-Bees. So the Brownian-Bees are the surviving particles, and each time one of the surviving particles branches, then we kill the surviving particle that's furthest from the origin. And what we end up with is that the particles in the Brownian-Bees at time t are given by, so x plus I of t is the position of the ith particle in the branching Brownian motion at time t. And then this is for I less than or equal to n plus t, which is the total number of particles in the branching Brownian motion at time t. But then in order to survive, we have to have the, so this is, this means the position of the ancestor at time s of the ith particle at time t. So the distance of the ancestor from the origin has to be at most mns for all times s between 0 and t. So that was our coupling with the d-dimensional branch Brownian motion. So the first thing I'm going to talk about is just briefly the proof of this result. Let's just recall that capital U and R infinity is the steady state solution of our d-dimensional free boundary problem. And let's let capital V of R be the integral over the ball of radius R of capital U. So then it turns out that capital V and R infinity is a steady state solution of our one-dimensional free boundary problem. And we can prove that solutions of our one-dimensional free boundary problem converge to this steady state solution, and we can also get control over how quickly they converge, and that's going to be useful later on. So this is what we can show. We can show that if we take a small positive constant c and a large positive constant k, and we take a small positive epsilon, then there's a time t epsilon that depends on c and k, such that if we take a function v0 from 0 infinity to 0, 1, the interval 0, 1, which is non-decreasing, and if v0 of k is at least c, and if v and r solves our one-dimensional free boundary problem with initial condition v0, then we can say that for a time t greater than or equal to t epsilon, then the difference between v at time t and capital V is uniformly bounded by epsilon, and also the difference between RT, the position of the free boundary at time t, and R infinity, the position of the steady state free boundary, is less than epsilon. And so this, once we've got this result, then that's essentially what we need to prove the long-term behavior of the d-dimensional free boundary problem. And that's because this result gives us really good control over RT for large values of t. It says that it's very close to R infinity. And that we can transfer back to the d-dimensional free boundary problem and say that holds for the free boundary for that problem, and then we can prove the long-term behavior. So I want to give you an idea of how the main steps in the proof of this result. So the first step is that you need to show that this equation star holds for two special solutions of the free boundary problem. So that it holds for V minus and R minus, which is the solution of the free boundary problem with initial condition given by V naught minus of R, which is C times the indicator that R is at least K. So that's an initial condition which is 0 and then jumps up to C at K. And also we want to show that it holds for V plus R plus, which solves the free boundary problem with initial condition given by V naught plus of R, which is just 1 everywhere. So that's the first thing you need to show. That's sort of the main part of the proof. And then the second step is, so it turns out that a comparison principle holds for solutions of the free boundary problem, in the sense that if you have two initial conditions, V01 and V02, that are ordered in the sense that V01 of R is less than or equal to V02 of R for all R. So V02 is above V01. And let's let Vi and Ri solve the free boundary problem with initial condition V0I for I in either 1 or 2. So then this comparison principle says that the solutions V1 and V2 stay ordered in the same way. So V1 of T and R is less than or equal to V2 of T and R for all times T and all R. And because capital R is the first point at which V reaches 1, that means that you get the opposite inequality for capital R. So you get that R1T is greater than or equal to R2T for all positive times T. So now let's suppose that we have a non-decreasing initial condition V0, which satisfies V0 of K is at least C. Then V0 is above V0 minus for all R, because we're assuming that it's non-decreasing and it's above V0 at K. And it's also less than or equal to V0 plus because it's at most 1. So that means that our comparison principle tells us that V of T and R is between V minus of T and R and V plus of T and R for all T and R. And also we get the opposite sandwich for the free boundary. So we get R plus T is less than or equal to RT, which is less than or equal to R minus T. So that means that because we've got that from step 1 that star holds for both of these special solutions, then for this general solution V and for RT, then star also has to hold. So that's roughly how we prove the long-term behavior of solutions of the free boundary problem. So now I want to go back to the Brownian bees. And so this is the result that I'm going to try and show you how to prove that's about the long-term behavior. So again, it's a one-dimensional result. It's just a result about the distances of particles from the origin. So we're going to take a large constant K and a small positive constant C. And then for a small epsilon, if we take our number of particles n to be at least some constant n epsilon, and our time t at least some t epsilon, then if we take an initial particle configuration xn in Rd to the n, such that under that particle configuration, Fn of 0 and k is at least c. So that means that the proportion of particles in the ball of radius k is at least c. Then we can say that if we condition on the initial particle configuration for the Brownian bees being xn, then the probability that the supremum over R of the difference between Fn of T and R and V of R, the probability that that's at least epsilon is less than epsilon. And also the probability that the difference between MNT, the largest particle distance from the origin, and R infinity is at least epsilon, that's less than epsilon. So I'm just going to tell you about the proof of this one-dimensional result. And then the way that that's turned into a d-dimensional result about the actual locations of particles in Rd is very similar to what I talked about in the last lecture, where we got to the d-dimensional hydrodynamic limit result. So you can sort of do a bit more work to turn this bound on MNT into a bound that is uniform over a time interval, and that then lets you compare the Brownian bees to a branching Brownian motion in which particles are killed if they go more than distance r infinity plus a little bit away from the origin. And that's a branching Brownian motion where particles are killed outside a deterministic boundary, and that's much easier to control. So I'm not going to go into that because it's fairly similar to what we talked about in the last lecture, but I'll try and give you an idea of how we prove this result. So first of all, we can assume without loss of generality that K is large and C is small. So we're going to do that. And now we're going to fix a large constant T, and we're going to take a time little t that's at least T. And first of all, we're going to suppose that Fn of little t minus capital T and K is at least C. So we're assuming that at least a proportion C of particles are in the ball of this big ball of radius K at time little t minus capital T. So then we can say two things. So the first thing we can do is use our one-dimensional hydrodynamic limit result to approximate the particle system on the interval little t minus capital T up to little t by a solution of the free boundary problem. And because that's a time interval of constant length, then our hydrodynamic limit result will give us a good bound if n is large enough. So what it says is that if n, the number of particles, is really large, then with high probability, Fn at time t is very close to Vn at time capital T, where Vn and Rn solves our one-dimensional hydrodynamic limit result with initial condition determined by the particle configuration at time little t minus capital T. So V naught of R is Fn of little t minus capital T and R. And here we're using the fact that I mentioned earlier that our bound on how close Fn is to Vn doesn't depend at all on what the particle configuration actually is at time little t minus capital T. And then the second thing we can use is what we had on the previous slide about how quickly solutions of the one-dimensional free boundary problem converge to capital B. So that tells us that if capital T is a large enough constant, then Vn at time capital T is very close to capital B. And that's because the condition that we needed to know how quickly the solutions got close to capital V was that we needed the initial condition V naught of K to be at least C. But here V naught of K is Fn of T minus capital T and K, and we're assuming up here that that's at least C. So that means that we now have that Fn at time T is with high probability very close to Vn at time capital T, which in turn is very close to capital B. So that tells us with high probability Fn at time little t is close to capital B. So now if we just have that this assumption that we made happens with high probability, then we'll be done. So what we now want to prove is this claim. So we want to prove that for a large time S, Fn of S and K is at least C with high probability. And when we've done that, then we'll essentially have proved this first statement here. And when you've got the first statement, then you can do a bit more work. So again, it's similar to something what we did in the previous lecture to get control on Mn. So once you've got this, then you can then get this statement by doing a little bit more work. So I'm now just going to try and explain to you how we prove this claim. So here's the claim at the top. So this is what we want to show. And I'm just reminding you that we're assuming that K is a large constant and C is a small constant. So what we're going to do, we're going to fix a positive time T naught, and then we're going to let Dn be the minimum non-negative integer I, such that Fn of n times T naught and K plus I is at least C. So what that means is, so I is the smallest non-negative integer that you need to add on to K, so that the ball of radius K plus I at this time n T naught will capture at least C times n particles. So I'm sort of trying to show that in the picture. So if you go a radius dn plus K from the origin, then inside that ball, you've got at least C times n particles at this time n times T naught. So what we actually want to show is that if little n is very large, then dn is equal to 0 with high probability, because that will say that we have at least Cn particles inside the ball of radius k. So the first thing that we're going to do is control the probability that dn makes a very large positive jump on a time step. So that's what we're going to do in this lemma. So we're saying that for a non-negative integer n and for a positive m, let's suppose that dn is less than or equal to m. So we have at least Cn particles in the ball of radius k plus m. Then, so I'm going to condition on, so I'm going to write ft for the filtration generated by the Brownian bees. So let's condition on the Brownian bees process up to time nt naught. Then the probability that dn plus 1 is bigger than m plus j is at most this thing for any integer j. So this is quite a rubbish bound if j squared is less than log n, because we've got this n out the front here. But it's quite a good bound if j squared is much bigger than log n, and that's how we're going to use this. So this is a bound on the probability that dn makes a positive jump that's bigger than j. So I'll give you a sketch of how we can prove this, and it's using our coupling with the branching Brownian motion. So first of all, we can just take n equals 0 with that loss of generality, just using the Markov property. So let's do that. And so we're going to use our coupling with d-dimensional branching Brownian motion. So we're going to suppose that an event holds for particles in the branching Brownian motion. So let's suppose that the location of the ith particle at time t minus the location of the ith particle at time t's ancestor at time 0. The LT norm of that difference is less than a third j for all times t between 0 and t naught, and all particles, so all I less than or equal to the total number of particles at time t. So that means that no particle in the branching Brownian motion moves more than distance a third j from its time 0 ancestor. So now we're going to split into two different cases, and in both of the cases, we're going to show that this event doesn't happen. So what that means here is that d1 is going to be at most m plus j. So the first case is, let's suppose that mnt is greater than or equal to k plus m plus a third j for all t less than or equal to t naught. So that means that in our branching Brownian motion, if a particle stays within this distance, within distance k plus m plus a third j of the origin for all times up to t naught, then it won't be killed. So that means that if you're looking at the descendant of a particle that starts in the ball of radius k plus m at time 0, then it's not going to move more than a distance a third j from where it started. So it's going to stay within this distance of the origin. So it's not going to be killed. So the descendants of all of these particles in this ball are going to survive. But how many particles were there in this ball at time 0? Well, because we're assuming that d0 is less than or equal to m, that means that we've got at least Cn particles in the ball of radius k plus m. So we're starting with at least Cn particles in this ball. None of their descendants are going to be killed, so they're going to have at least C times n descendants. And all of their descendants are going to end up in the ball of radius k plus m plus a third j, because none of them are moving more than this distance from where they started. So we've got more than Cn particles in this ball, and so that means by the definition of dn, that means that d1 is at most m plus a third j, and so in particular it's less than m plus j. So that's one possibility. And then the other case is that this doesn't happen, which means that there must be, so mnt star must be less than k plus m plus a third j for some time t star less than or equal to t naught. So then that means that at this time t star, all of the surviving particles in the branching Brownian motion that haven't been killed have to be in the ball of this radius. So they have to be in the ball of radius k plus m plus a third j, because this is the maximum distance of a surviving particle from the origin. And now if we take an I less than or equal to n plus t naught, then if we look at the distance between the ith particle at time t naught in the branching Brownian motion and its ancestor at time t star, then just by the triangle inequality, that's at most the distance between the ith particle at time t naught and its ancestor at time 0, plus the distance between the ancestor at time 0 and the ancestor at time t star. But then by our assumption up here, this distance is at most a third j, and this is also at most a third j because the ancestor at time 0 is also the ancestor of this guy at time t star. So this is at most 2/3 j. So that means that because all surviving particles are in this ball at time t star, and then any surviving particle at time t naught, its ancestor at time t star is at most 2/3 j away. That means that all of the surviving particles at time t naught have to be in the ball of radius k plus m plus j. So that means that in particular that means there are n particles in this ball, but in particular there are at least c times n particles in this ball. So again, that means that d1 is less than or equal to m plus j. So in both of these cases, we've got that this happens. So now in order to get our result, we just have to show that the probability that this doesn't happen is at most this. But that's not too hard to show because this is just an event for particles in a branching Brownian motion. So this is saying that, so we just need to control the probability that there is a particle in the branching Brownian motion that moves more than a third j from its starting position. And that probability is at most the expected number of particles in the branching Brownian motion, which is n times e to the t naught, because you start with n particles and you're running the branching Brownian motion for a time t naught. And then you need to multiply by the probability that a single particle moves more than distance a third j from its starting position if it's moving according to a Brownian motion. And a Gaussian tailbound will let you show that you get at most 4d times this thing. So that's a sketch of how we prove this lemma. And then the other thing that we need, so that bounds the probability that dn makes large positive jumps. What we can also use is the free boundary problem approximation to actually show that with high probability, if dn is bigger than 0, then it actually makes a negative jump. So what we can show is that if t naught is a large constant, then if m is greater than or equal to 1, then if our initial condition for our free boundary problem satisfies v naught of k plus m is at least c, then if v and r solves our free boundary problem, then v of at time t naught of k plus m minus 1 is at least 2c. So roughly what this is saying is that if the initial condition for the free boundary problem puts mass at least c within this big distance k plus m of the origin, then the mass grows and spreads enough that a time t naught later, there's at least 2c mass within a slightly smaller distance of the origin. And then once we've got that, we can use our one-dimensional hydrodynamic limit result to say that for m greater than or equal to 1, if dn is less than or equal to m, so that means that there are at least cn particles in the ball of radius m plus k. So then that means that for our one-dimensional hydrodynamic limit result, the initial condition will satisfy this. And so we'll be able to say, compare our particle system to a time t naught later to something that satisfies this. So that lets us say that with high probability, dn plus 1 is at most m minus 1. And with high probability means with probability 1 minus something that's much less than n to the minus 1. And that's because the probability bound in the hydrodynamic limit result was much smaller than n to the minus 1. So we've got this very high probability that dn makes a negative step, and then we can use the lemma. We use it for values of j at least log n to the 2/3, where it's then quite a good bound. to say that the probability of making really huge positive jumps is very small. So I won't go through the details of this bit, but those two things together let you couple dn with a positive recurrent Markov chain that we could call yn, in such a way that dn is less than or equal to yn for all n. And so by taking capital N to be large enough, you can put enough mass of the stationary distribution for yn at 0 that the probability that yn is equal to 0 is at least 1 minus any small epsilon that you want for n very large. So that means, so now we have that if yn is 0, then because of this, dn has to be 0. And by the definition of dn, that means that fn of nt naught and k is at least c. And this means that this happens with high probability for large n. So that's basically what we wanted for the claim. So for the claim, we wanted this to hold for an arbitrary large s rather than a multiple of t naught, but that's quite easy to get from this. So that's kind of a sketch of how we proved the claim, which then gave us the long-term results for the Brownian bees. So that's all I'm going to say about the Brownian bees today, and that's actually the last proof of the lecture. So if you're all sort of proofed out, then now it's just going to be some overviews of an overview of some results and some conjectures. So for some other related branching selection systems. So the first one that I want to talk about is a very closely related particle system called the barycentric Brownian bees. So this was studied by Luigi and Jessica Lin and Thomas Tondron in a paper last year. So in this system, we have n particles that are moving around in RD according to independent Brownian motions, and they're all branching at rate 1. And whenever a particle branches, then the particle in the system that's furthest from the center of mass, or the barycenter of the system, is killed. So the difference with the Brownian bees that I've been talking about so far is that rather than killing particles that are furthest from a fixed point, the origin, it's particles that are furthest from the center of mass of the system. So again, I'm going to write xn of t for the vector of particle positions at time t. And I'm going to write x bar of t to be the barycenter of the particle system at time t. So it's 1 over n times the sum from k equals 1 to n of xn k of t. So the sum of all the particle locations divided by n. So what they prove is an invariance principle for the trajectory of the barycenter. So they prove that if you fix the number of particles n, then there exists a constant sigma that depends on the dimension d and on n, such that, so if you take the position of the barycenter at a time t times m, and then you divide by the square root of m, so you're doing a diffusive scaling, and if you let t range between 0 and 1, then as n tends to infinity, this trajectory converges in distribution with respect to the Skorohod topology to sigma times bt, where bt is a Brownian motion. And what they conjecture is that actually, if you look at, so for the large n long-term behavior, if you look at the positions of the particles recentered by the position of the barycenter, then actually you should have the same behavior that we see for the Brownian bees, in the sense that if you take a large n and you take a large time t, then if you take a subset A of RD, then with high probability, if you take 1 over n times the number of particles, where if you take the particle position at time t and take away the position of the barycenter, then that's in the set A, then that should be close to the integral of capital U over the set A. And also, if you take the maximum over all the particles of the distance of the particle's position to the barycenter at time t, that should be approximately R infinity. So this should be for capital U and R infinity, exactly as I've been saying up till now, so the steady state solution of the d-dimensional three boundary problem. So then in some ways the Brownian bees is also a special case of a more general particle system. So it's a special case of a general d-dimensional NBBM. So these models were introduced by Nathaniel Beresticki and Li Zhizhao in a paper in 2018. So they have a fitness function f on the whole of Rd, and we can think of the fitness value of a particle in the system that's at location x is f of x. And then again, the system consists of n particles that move in Rd according to Brownian motions and branch at rate 1. And each time a particle branches, then the particle in the system with the lowest fitness value, as measured by f of its location, that particle is killed. So again, there are exactly n particles in the system at all times. So if we took a fitness function that was decreasing in distance from the origin, so for example, f of x is, if f of x was minus the L2 norm of x, then we would just get the Brownian bees process. But Beresticki and Zhao, they actually consider two very different cases of this model, both of which end up pushing the cloud of particles away from the origin. So they look at the case where f of x is the norm of x, so the further a particle is from the origin, the higher its fitness. And in that case, what happens is that the particles end up forming a clump that moves away from the origin at a deterministic speed and in a random direction. So you might sort of initially think that what should happen in this case would be that the particles would be sort of evenly distributed around the boundary of a ball, which would be getting sort of further and further from the origin. But actually what ends up happening is that there's sort of one direction where a few particles end up doing a bit better, and that means that they sort of have more chance to branch and spread, and so other particles in different directions end up being killed, and so eventually that sort of clump of particles that did well end up taking over the entire population, and the entire population is a single clump that moves off in one direction. So that's quite a nice result, I think. And then the other case that they look at is the case where f of x is the scalar product of some fixed vector lambda and x. So in this case, maybe as you might expect, the particles form a single clump that moves in direction lambda away from the origin at a deterministic speed. And then so we conjecture that actually for this general NBBM, there should be a hydrodynamic limit, which is the solution of a free boundary problem. So let's let omega L be the set of x in Rd such that f of x is bigger than L. So it's the set of locations where the fitness is bigger than L. So then this ought to be the free boundary problem that gives the hydrodynamic limit of this particle system. So it should have two unknowns, u and L. So u would be a function of time t and x in Rd, and L would just be a function of t. We should think of u of t and x as being the density of particles at time t and location x. And we should think of L of t as being the minimum fitness in the population or in the particle system at time t. And then they should satisfy this system of equations. So du by dt should be half the Laplacian u plus u for x in the region where the fitness is bigger than L of t. And u should be equal to 0 outside that region, so also on the boundary of the region. And the integral of u at all times t should be equal to 1. And then u should also have some initial conditions, some probability measure mu naught. So this is what the hydrodynamic limit should be, but in fact, not even have we not shown that this is the hydrodynamic limit. It's actually also not clear that in general, whether in general the solution to this system of equations even exists or is unique. But this is what the hydrodynamic limit should be. So now I'm going to move away from branching selection systems in continuous time and talk a bit about a discrete time branching selection system called the n-particle branching random walk. So this is the n-particle branching random walk. So let's let x be a real valued random variable. So we'll call the distribution of x the jump distribution. And the system is going to consist of n particles with locations on the real line. And it's going to be a discrete time process. So we're only going to see the locations of the particles at integer times. So at each time n in the non-negative integers, each particle in the system has 2 offspring. And each of the 2n offspring particles makes an independent jump from its parent's location with the same law as this jump distribution x. And then after all the offspring particles have made these jumps, then the n rightmost particles out of the 2n offspring particles form the particle system, or the population at time n plus 1. So on the right, I'm showing you what the n particle branching random walk might look like for n equals 3. So first of all, each of our 3 particles has 2 offspring, which each make a random jump from the location of their parent. And then we see which of these 6 offspring are furthest to the left. So that's these red particles. These particles are killed, and these particles, these n rightmost particles, form the population at the next time step. And we're going to write x1n of little n, x2n of little n, and so on up to xnn of little n for the particle positions in the n particle branching random walk at time little n. And actually it's convenient to have these ordered so that x1n of n is the leftmost particle, and then this is the second leftmost particle, and so on up to the rightmost particle. So first of all, there's quite a lot known about the asymptotic speed at which the cloud of particles moves to the right. So if the jump distribution has finite mean, then there's a deterministic Vn, such that if you take the position of the rightmost particle at time n and divide by n, that converges as n goes to infinity to V capital N. And also if you take it converges almost surely and in L1. And if you take the position of the leftmost particle at time n and divide by n, that also converges almost surely and in L1 to this deterministic V capital N. So it's an asymptotic speed that depends on the number of particles. And then a result of Berard and Gouret gives a nice result about the asymptotics of V capital N as n goes to infinity. So they show that if the expectation of e to the lambda x, where x is the jump distribution, is finite for some positive lambda, so if x has some exponential moments, and there's a couple more technical assumptions, then the limit as as capital N goes to infinity, Vn converges to a limit, which we'll call V infinity. And also V infinity minus Vn as n goes to infinity goes like a constant times log n to the minus 2. So that means that the asymptotic speed at which the cloud of particles moves to the right converges to a constant as the number of particles goes to infinity, but it converges extremely slowly because log n to the minus 2 only goes to 0 extremely slowly as n goes to infinity. And this result was actually conjectured in the physics literature by Brunet and Derrida in 1997. And it's thought to be part of a wider phenomenon. So there's a related result for an SPDE, that's the Fisher-KPP equation with noise. That's due to Muller, Mitnick, and Castell. So that's the asymptotic speed if the jump distribution is fairly light-tailed. Someone's asking if there's a result about the scale of spread of particles. So you can show that, let me think. So I think you can show that it's at most log n. Yes, and I think they actually do that in this paper. Yeah, I'm pretty sure that they show that it's at most log capital N, and that result is in this paper. So that's what's known about the asymptotic speed. But what I mentioned back in the first lecture is that one of the things that we're really interested in for these branching selection systems is what's the behavior of the genealogy, or the family tree of a sample of particles. So what we'd like to do is fix an integer k, and then we'd like to suppose that n is really, really large, so we've got a very large population, and we want to sample k particles uniformly at random from the capital N particles in the n particle branching random walk at a large time t. And then we want to trace their ancestry backwards in time. So what we'd end up with is a process Pn of partitions of the integers 1 up to k, where I and j are in the same block in the partition Pn, if and only if the particles, or if and only if the ancestral lineages of the particles that were sampled with labels I and j have a common ancestor at time n before time t, so at time t minus n. So we might draw this as something like this. So we might start by sampling 5 particles, we trace them backwards in time, and then at this time, so after going this time back in the past, then these 2 ancestral lineages were both offspring of the same particle that had 2 offspring at this time, and so on. So we go all the way back until we only have 1 common ancestor for all of the particles in the sample. So it's conjectured that the scaling limit of the genealogy under some conditions for the n particle branching random walk is given by a special coalescent process called a Boltzhausen-Schnittmann coalescent. So no, a Boltzhausen-Schnittmann coalescent, if you have B blocks in total in your partition, then for any given k tuple of blocks, those k blocks all merge together into one at a particular rate that's given by k minus 2 factorial times b minus k factorial over b minus 1 factorial. So this particular rate is not going to be very important to us, but this is a picture of a simulation of a Boltzhausen-Schnittmann coalescent started with, I think, 50 lineages from Anton Bokolbinger and Götz Kersting. And you can see from the picture that there are times in the Boltzhausen-Schnittmann coalescent where, so like this time, where a significant proportion of all of the lineages all suddenly merge together at the same time. So then, as I said, it's conjectured to be the scaling limit of the genealogy of the n particle branching random walk. So this conjecture is due to Brunet, Derrida, Muller, and Meunier, and it says that so roughly it says that if the jump distribution x has exponential moments, so if it's light-tailed enough, then the genealogy of a sample from the n particle branching random walk on a log n cubed timescale converges to a Boltzhausen-Schnittmann coalescent as n tends to infinity. And this is also believed to be the case for the NBBM. So it might seem kind of surprising that that the scaling limit of the genealogy would be this coalescent in which lots of ancestral lineages can all merge at the same time, because in the n particle branching random walk and in the NBBM, each individual can only have 2 offspring at one time. So in the actual coalescent process, then all of the mergers must happen pairwise. But the reason that you can still have the Boltzhausen-Schnittmann coalescent as the scaling limit is that you're looking on a log n cubed timescale. So what it would mean is that there are times at which, during a time that's much shorter than log n cubed, there are a lot of pairwise mergers that happen during this sort of shorter time interval. And so then on the log n cubed timescale, then it looks like that all of those mergers happen simultaneously. So this is just a conjecture, but what has been proved by Beresticki, and Schweinsberg is if you look at a branching Brownian motion with drift that's minus square root of 2 minus something small, then so this is a branching Brownian motion where each Brownian motion has this negative drift. And particles are killed if they hit the origin. And if you take a suitable initial condition, then over the relevant timescale for the genealogies, then the population has size roughly n. And that's it has size roughly n because of this this clever choice of the drift. And what they show is that oh, sorry, someone's written what does it mean for NBBM? So the models do seem quite different, but actually on this kind of scale, then they should have the same behavior. So it's conjectured that also if you sample, so again, your NBBM consists of n particles, so you can sample k of them at a large time, trace their ancestry backwards in time, and again, you get a coalescent process. And it's conjectured that for that coalescent process as well, if you rescale by a log n cubed timescale, then you should get a Boltzhausen-Schnittmann coalescent. So it's meant to be a very large phenomenon that if you take one of these models that is modeling a population under selection, then a very large class of models should have this Boltzhausen-Schnittmann behavior. So what Beresticky and Feinsberg prove is that for their model, if you sample particles at a constant t times log n cubed, then if you rescale time in the genealogy by 2 pi over log n cubed, then the genealogy converges to a Boltzhausen-Schnittmann coalescent as n goes to infinity. So this process, because the population has size roughly n, then it ought to have the same characteristics as the NBBM and also the n particle branching random walk. And for that process, they can actually rigorously prove convergence to the Boltzhausen-Schnittmann coalescent. So that's what the genealogies ought to look like when the jump distribution x is light-tailed and has exponential moments. But so the n particle branching random walk has quite different behavior if the jump distribution is heavy-tailed. So let's suppose that the probability that the jump, so x is the jump distribution, and the probability that capital X is bigger than x, let's suppose that goes like x to the minus alpha as x goes to infinity for some positive constant alpha. So then the asymptotic speed is known. So this is a result of Berard and Maillard from 2014. So they show that if the jump distribution has a finite mean, then if you take the position of the rightmost particle at time n and divide it by n, then that converges as little n goes to infinity to the asymptotic speed v capital N. And they show that as capital N goes to infinity, so the asymptotic speed of a cloud of capital N particles, that goes like a constant that depends on alpha times n to the 1 over alpha times log n to the 1 over alpha minus 1 as n goes to infinity. So in particular, this asymptotic speed goes to infinity as capital N goes to infinity. So it's very different behavior to the light-tailed case where we had that Vn converges very slowly to a constant, because here, if you add more and more particles, then the asymptotic speed of the cloud of particles goes to infinity. And if instead the jump distribution has infinite mean, then they show that the cloud of particles actually accelerates. And then it's also known what the genealogies look like. So this was joint work with Matt Roberts and our PhD student, Sophia. So if you sample k particles from the n particle branching random walk with a heavy tail jump distribution at a time that's at least a constant times log n, then if you look at the genealogy on a log n timescale, then it's approximately given by a star-shaped coalescent when n is large. So what do I mean by a star-shaped coalescent? Well, I mean that there's a time at which suddenly all of the ancestral lineages all coalesce into a single lineage all at the same time. So what that actually means for the n particle branching random walk is that you have to go back in time at a random time that's between log 2n and 2 log 2n. And then once you've gone back that amount of time, then there's a time interval that lasts little o of log n, such that all of the coalescence to the most recent common ancestor happens in that time. And the reason that happens is that every now and again there's a particle which makes a really big jump, and that particle gets so far out in front of the rest of the population that all of its descendants manage to totally take over the population. So this is, again, it's really different behavior to what's conjectured for the end particle branching random walk with a light-tailed jump distribution, because it's the genealogy is on a different time scale of log n rather than log n cubed, and it's a star-shaped coalescent rather than a Boltzhausen-Schnittmann coalescent. So I just want to end by showing you a video, because my student, no, I'm failing to, there we go. Because my student Sophia has made a really nice video of what the end particle branching random walk looks like under some different jump distribution assumptions. So let's take this back to the beginning. So the circles represent particles in the end particle branching random walk, and it's for 3 different jump distributions. So the red one is the heavy-tailed jump distribution that I've been talking about on this last slide. The blue one has an exponential tail for the jump distribution, so it's more the light-tailed type behavior. And then the yellow one has a stretched exponential tail for the jump distribution, so it's sort of somewhere between the two. And I think it's a nice way to see the really different behavior that you get, because you'll see in the red in the red system that there are sometimes really big jumps that then their descendants end up taking over the population, whereas the blue system looks really different. So it's just going to sort of repeat a few times, but so you can see now that there's just been a really big jump in the red particle system, and then everything sort of caught up with that, whereas the blue one is just kind of inching along in a very different way. So I quite like this video, so I wanted to end with that. So I'm going to stop there. So thanks very much.
Okay, thank you. And I think we can all unmute and thank Sarah for the wonderful lecture. And we have time for questions and discussion.
Well, I've got a question, but I always feel like I'm jumping the line. If that's
Go
true.
ahead.
If I'm recalling correctly, when you've got in the continuum setting with, you've got FKPP, and you can kind of interpolate by adding those Allen-Kahn terms, and conjecturally get coalescents of various types, interpolating all the way from Kingman to Boltzhausen-Schnittmann. Is there a natural way of kind of softening the selection with these discrete models that might kind of have that same interpolation?
Yes, so that is something that I was talking about recently. So so let me see if I can remember correctly. So so this is something that I talked to Eric Brunet about recently. So these ideas are his rather than mine. But he was suggesting that what you can do is say you can have some kind of moving barrier that means that if particles hit that barrier, then they reflect off it. And if you, depending on how you vary the speed of that barrier, you can end up with a pushed wave rather than a pulled wave. So you can end up with particles that are at the back sort of managing to do better than sort of having a faster or driving the system along.
Oh yeah. Oh yeah. Okay.
So and then you get a different free boundary problem, and the idea would be that then you get pushed waves rather than pulled waves behavior, and so then potentially you would get a different coalescent process.
What is a pushed wave as opposed to a pulled wave?
Yeah, so those are different traveling wave solutions of PDEs. So it's called a pulled wave if it's sort of driven by what happens in the tip of the wave. So actually what it means is that the speed of the wave is the same as it would be if you just took the linearized equation, or that's kind of what it means. But a pushed wave, the sort of the fastest rate of growth is further back. It's not in the tip of the wave.
which kind of that corresponds to like whether selection. Actually, never mind.
So, well, yeah, I mean, it does correspond to something in the population in a way, because if it's a pooled wave, then you're sort of doing better if you're in regions where your type or whatever you are is rare. So it's sort of, if you have a pushed wave, then maybe you're in a situation where there's some kind of cooperation going on, or you're better off being not in the tip of the wave.
I was also wondering, is there like a solid obstacle to using the Beresticki-Schweinsberg? Does their method not at all ready to do the MBBM, for example, to prove convergence of the coalescence? Will it break?
Yeah, so I mean, it doesn't carry out. Yeah, I think. So it does rely on the fact that it's a deterministic boundary that you're killed if you hit.
Right.
So yeah, so you definitely can't carry it immediately over, but it still kind of tells you something about heuristics for why it should be true for the NBBM.
Hi, Sarah. Thank you for the course. I have a question, or more general. I was wondering, what are the parts where you cannot use these nice couplings and probabilistic methods, and you can only use like PD theory? You said that you were only going to show the probabilistic part. So what are you hiding from us?
Well, so I guess you have to do quite a lot of PD work to actually show that the solutions of these free boundary problems actually exist. And so, and I guess there was also some PD stuff where, so I just, when I was talking about how solutions of the free boundary problem converge, then I didn't really tell you that. I mean, I only told you the sort of the main steps of the proof. So there's quite a lot to that proof that is, well, it's kind of a PD result, but then in a way you can sort of prove it using Feynman-Katz formula for the solutions of the PDE. So it's not sort of totally PDE work, but you do have to do some PDE proofs. So I guess that's maybe where I was hiding stuff.
That's great. I appreciate it. And my other question is, what is so special about this log n square timescale? Like it appeared, well, if you have an answer to that, maybe it's a vague question. If there is a short way to say this is the right scale.
Oh, you mean the log n cubed?
Yes, the log n cubed, sorry.
Yeah, so I kind of think that it comes from, so I think it's kind of connected to the fact that you can have, so it's kind of connected to consistent maximum displacement in a branching Brownian motion I think in a sort of weird sort of way. So it's connected to the fact that there is a particle in a branching Brownian motion that stays consistently within distance t to the third of the rightmost particle. And that's sort of as close as you can stay. And that's very connected to Berard and Gouret's proof of this asymptotic speed. And I think their proof kind of also hints at log n cubed being the right timescale for the genealogy. So I think, at least the way I understand it, they're all connected.
You mentioned this where you say the difference between V and to V infinity, it converges as some log n. Yes.
Log n from 2, yeah.
Okay, so that's the hit, and then that's the scale that gets everything right. Okay.
Yeah, I think so, but
yeah, it's quite of vague because sometimes there's not like a short answer to say why this works. Sometimes it works.
Yeah.
Yeah. Okay, thank you.